The subject of today is continuum knowledge models. As I told you, after these two lectures, we have been working on the fundamentals, the thermodynamic fundamentals of constitutive modeling. Now we are applying them to the first family that we are going to study in this course, which are continuum damage models. Well, continuum damage models is a relatively recent family of models. When I did my PhD, for instance, nobody talked about that. That didn't exist. So, but however, since a number of years ago, they have been widely developed. Excuse me, can I have your attention? They have been widely developed because, I mean, a number of materials are amenable to be modeled using these models. Typically, materials which are called geomaterials, materials that have a microstructure or a mesostructure which is made of a matrix and some aggregates or some little particles, typically concrete in civil engineering, but also some materials in soil mechanics are frequently modeled with this kind of models, and also some more less traditional materials are now modeled with continuum damage models. So they are, from one side, they are very simple. You see that are very simple to use. At the end of the day, when we just next day we are able to implement the algorithm for modeling such a material in a code, you will see that the implementation is very short, very straightforward. And on the other hand, they can model many different aspects that we observe, many different phenomena that we observe in some of our materials that we want to simulate. Well, let's have a first approach to this type of behavior by this sketch of the behavior of a material. Imagine that you have a material piece of a material, and that we subject this material to the action of a tensile stress, which we know is producing an exterior, let's call it apparent stress, which is the ratio of the force, applied force, divided by the surface of application of this force. So the cross-section, so to speak. Okay? Okay, let's imagine that we increase this force and then this apparent stress that we call sigma, and from zero, and we increase it more and more and more. At a certain stage, at a certain point, for a certain value of that, some possible defects in the internal structure of the material intensify these stresses a little bit in some points, so some type of failure occurs inside the material, which can be translated as the existence of cracks that lose its cohesion, and then that means that at a certain stage we can have a situation like that. In a typical cross-section, we have some part of the microstructure of the material that is cracked, that lose the capacity of carrying stresses, and some other part that it's already completely intact. So let's quantify these two parts. Say, okay, imagine that if S is the value of the area of the cross section, there is one part, this stage that we are considering, that this section that it's not able to resist any stresses anymore because it has failed before this stage. This is what we denote by SD, the damaged section, the damaged part of the area that is smaller than S, by the way, than the total section, but that is this area, and we consider that in fact there is no contribution to sustain the stresses of this part of the area. On the other hand, we have a rest of the area, so it would be the total section plus SD, which we assume it's completely able to sustain the stresses, and that is responsible from the fact that exteriorly we can apply, we have still some capacity, some carrying capacity of the structure. Okay? Well, so we introduced the terms damage section, SD, the area of the damage part of the cross section. The effective section, which we'll denote by a bar, which is the total area, S, minus the damage surface. Okay? This is supposed to be positive. Of course, that this damage surface is never greater than the total area. And then we introduce the effective stress as the stress that effectively is resisting that section. Okay, that section, imagine that the behavior of the material here is purely elastic in 1D. So at this point, since it's not broken already, it's able to sustain the stresses, and these stresses react in terms of the strains as an elastic material does. So the stress, sigma bar, is proportional to the strain through the elastic modulus epsilon. That's a simplification. We can make intervening the Poisson ratio and so on. We are doing it simpler. I'm just trying to make a phenomenological approach. By the way, the total force that we exert from the exterior to this cross section by equilibrium, which is the product of the upper stress times the total section, F equals sigma times S, by equilibrium has to be just equilibrated by this effective stress multiplied by the effective part of the stress, the resisting, the non-damaged cross section. So, which is sigma bar. So we have this equation, which is equilibrium, from which we can obtain which would be the apparent observer stress that we observed in the experiment. In the experiment, we imagine that we don't have any mean to obtain or to see what is happening inside. We just can obtain exteriorly, whenever we apply a force, then we obtain a stress, which is that one. We don't have any access to this one. So we can say that the apparent stress from this equation, sigma, is equal S bar divided by S multiplied by sigma bar, the effective stress. Okay? Well, just by expressing the damage stress or the effective stress as the total minus the damage stress, that's the inequality that comes from here, and dividing by S, we obtain this formula here. That says something which is in the spirit of these continuum damage models. That something is that if we look at what is the stress, the macroscopic stress, the stress that we observe from the exterior, the apparent stress, and you want to relate that to the strain that is subjected to this specimen, which is also can be measured macroscopically, for instance, measuring the ratio of the increment of length per unit of length. So that's something that we can guess macroscopically. It's related to this with this expression, 1 minus one factor, which is a scalar, by the way, which is the ratio of the damaged surface with respect to total surface. From now on, we call that the damage variable, times the effective stress, which is the stress that an elastic material would resist from this strain, which is E times epsilon. Okay? So this is the fundamental equation that we extract from this first approach. The apparent stress, the one that I'm observing from my experiment, is the theoretically elastic stress or effective stress, which is the one that we would obtain if there was no damage, multiplied by a factor 1 minus d. D being a factor that is evolving a long time, depending on the evolution of the forces. It's not constant. We can say that E is constant, but not D, for instance, not a material property. This factor has some properties that we are going to examine now. But this is the fundamental equation we are going to see. Okay, so what else can we say about this? Okay, well, this damage variable evolves along time first. And is a function of something that evolves, which is the damage part of the surface. You can imagine that this damage part of the surface initially is 0. So initially the material is completely undamaged. This damaged surface is 0. And then at a certain point, the material is also able to sustain stresses in an undamaged stage up to a certain point. Beyond a certain point, due to certain perturbations, microscopic perturbations, whatever it is in there, this damage starts appearing, and the value SD, which initially is 0, starts evolving. And probably, if we keep increasing the loads, or at least the strains, then that damage also propagates, and this surface also increases. But there is a maximum value for this, which is when SD, the damaged surface, is the total surface. At this point, we should expect to have completely broken a specimen and the carrying capacity of the specimen be reduced to 0. Okay? So then what we can say is that this damage value, due to that, and the definition of the damage value, by dividing all this equation by S, you take that D, the damage value, ranges from 0 at the initial stages for the undamaged material to a maximum of 1. Okay, so that's a limitation that comes from the physics that we have studied. So we can talk about an undamaged stage that doesn't correspond to 0 stresses. Maybe this undamaged state also takes place for certain value of the stresses, which are not necessarily 0, but maybe below a certain threshold. And also the damage evolves, D is missing here, in terms of this ratio, and the maximum for fully damaged state is when damage variable is 1. So D is one scalar variable. There are more complicated models which, starting from that, develop damage models which depend on more than one damage variable, accounting for an anisotropy and so on. We are just restricting ourselves in this analysis to isotropic damage models in which we have just one damage variable. Okay. Well, so this is the approach. Okay, this is the idea, and now we are going to do some abstraction, and we are going to generalize this idea to not such a simple case like this one, having just one component of the stress and so on. Before doing that, maybe we can add some additional properties that you have to impose on our model about the damage variable D. For instance, what about the evolution of D? D dot, that means the evolution, the increment per unit of time of the damage variable, according to that equation, this is constant, is the increment of the damage surface per unit of time divided by S. Of course, in principle, that could be greater than 0 or smaller than 0. Again, the situation in which this is smaller than 0 would correspond to some healing of the material, which in this family of materials doesn't happen. So we know that once the material is broken, it doesn't recover the cohesive capacity at the lips of the form cracks. Or at least we assume that. And by the way, this, which is an assumption that we observe from our perception as engineers, or as physicists or mathematicians, from the experiment, is something that is going to be told from our model using the second principle of thermodynamics. I anticipate that. But now, for the time being, as we can say that we don't see as physical the possibility that S dot D is smaller than 0, which would be that the damaged surface is reduced reduces spontaneously. There is a self-healing. So this is not something that we consider, and this translates into that d dot is always greater or equal than 0. So we can produce damage, increase that a long time as we increase the strain, for instance. Damage which initially was 0, finally will be 1, but we can increase that in a continuum monotonic manner, never decreasing. It's not possible that this evolution of damage along times goes that way. Okay? We have to impose that. Also, this damage, sometimes we use the word degradation of the material, it doesn't necessarily initiate at the beginning of the strain history. There is a threshold below which the material doesn't experience any damage, and after this threshold we have an initial damage or an evolution of this damage. We'll talk about how much is this evolution. I'm not saying anything about this evolution. Okay? Well, this threshold would be either in stresses, epsilon 0, or maybe in strains or in stresses. We'll talk also about that. Okay, so now let's synthesize what I have said for 1D cases. We imagine that, again, if we plot stress versus strain, the model that I have idealized, we have just a sketch so far, can be expressed as that. The stresses are proportional to the strains through would be E times epsilon would be the elastic stresses, the stresses that would correspond if there is no damage, but affected by a factor that in fact can be considered that this factor, 1 minus d, which is positive, is applied to the Young modulus. Okay? Or this being a second or damaged or degraded second modulus. So the total stresses and the total strains are affected by a varying second modulus, this is the second modulus, which is evolving from an initial value, which is when d is equal to 0 at the very low values of the strains of the stresses that we call the elastic regime, and it evolves from the initial value when d is equal to 0, which is the Young modulus, the lasting modulus of the material, but beyond a certain threshold, it initiates, it starts degrading following a certain law, and this second modulus being smaller and smaller and smaller. Okay? So we can look at this stress, total stress versus total strain as an elastic-like constitutive equations with the second or the Young modulus being degraded due to damage, due to this evolution. By the way, for instance, the fact that d is always increasing means that this evolution, this Young modulus can never increase. This second modulus can never increase. Okay? For instance, it would have no sense that the curve would be like that, in which the Young modulus increases. That means that even if you go that way or that way, the Young modulus always decreases. The second Young modulus always decreases. Look that we can talk about the elastic branch, and with the degradation is 0. The damage modulus, the damage parameter is, or damage variable is 0. And beyond that, any nonlinearity, or the degradation of this d dot, the fact that beyond that point we have having an increasing value of the evolution of the damage variable translates into nonlinearity of the behavior. Again, don't think that this is a linear relations between the stress and the stresses, because this is not constant. The second Young damage, the second Young modulus depends on the history of the strain, so it depends implicitly on the strain. So this is not a linear model anymore. It's only linear up to this point here, double stresses, double strains, triple stresses, triple strains, but beyond that point is no longer linear. Okay, at the very end of the story, when the material is degraded even going so far as we can imagine. Finally, when d reaches the value 1, that means that this secant modulus goes to just 0. 1 minus d is 0, and then the capacity of the material to sustain stresses qualified in terms of the Young modulus becomes 0. When epsilon d, when d is equal 1, sigma is necessarily 0, no matter how big is epsilon. Yeah.
Regarding the Young model, the damaged one, why is it proportional? I mean, like.
I didn't say it's proportional. What do you mean it's proportional? When do you see? Where do you see here? D is proportional to what? Yeah?
Yeah, it seems that it's like a linear.
Why? I don't see this. I see that according to that equation, d is constant and 0 in this branch. Okay. Then it varies. I don't say if it's linear or non-linear or exponential or whatever. I don't say anymore. And for so far.
I mean the other line that is straight, the ED.
ED. Well, ED is not linear. Well, I mean, this is part of the model. 1 minus d, the fact 1 minus d, is just comes from the approach I've done. So that approach says that finally the fundamental equation that I'm going to impose is sigma equal 1 minus d times E times epsilon. No minus d squared or minus d to the logarithmic. Of course, I can make a change of variable and consider that.
According to the drawing, it's like straight line.
Not, I don't see why you insist in straight, because it just, if you mean that here it's a linear dependence on d, doesn't mean that everything, the stress and the strains, because d depends on the epsilon too. And I'm not saying how is it dependent. Okay? Okay. So anyway, thanks for the question. I think it can help other students that maybe are a little more shy than you to ask it. Okay, so this is the plot. Look, another question is the following. What happens is at a certain point, so I increase the strains. Imagine I increase the strains, the material reaches this stress, then maybe it can go this way, but we'll talk about that too. The material at a certain point decreases its stress capacity and goes this way. That's what we call a softening branch. We'll talk about that. But imagine that at a certain point I decide to release the strains, the stretch. So once I'm here, I want to release beyond this point, I want to release the strains, or I release the strains. Shall the material go this way? What would happen if the unloading process in terms of the strains, it's corresponded, or it's the stress counterpart is such that we return by the same way that we have arrived to this point. So that means that that slope would increase. If the slope would increase, that means that d decreases. Okay? So that is against that assumption here. So d dot always is greater or equal than 0. So never, this is not compatible with the fact that we come back to this way. So if this way is not possible, the only way is that, so the way d is smaller than 0 is that, which is not possible. The way d is greater than 0 is that, which is not considered here because I'm supposing that I'm unloading. So what is the remaining option? D equal to 0, d dot equal to 0. So no evolution of the damage, which corresponds to an unloading branch, which is that. So what I'm saying is that at this point, I decrease the strains, then d dot will be 0, so d will remain constant, and this factor will remain constant while I am decreasing the strains. Okay? So that ED will remain constant. So the unloading will take place along a second branch, second to the origin. Okay?
This could correspond to the unloading process?
Yeah. Well, this is a we have not defined yet the concept loading and unloading strictly, but of course, this part here is what we call elastic loading. This part here will correspond to what we will term inelastic loading, and that is what we will call inelastic unloading. Elastic unloading, sorry. Elastic unloading. Why elastic? Because we'll prove that here there is no dissipation. And it behaves in this branch, while I'm keeping the stress state, strain state in this branch, it's like an elastic proportional, incrementally proportional.
But this is not the elastic range. Why we call it elastic loading?
We'll see.
How could it be that if the stress is zero, the strain is zero, if there is damage?
Well, look at that. Imagine that during this process, we cannot vary this factor. What I'm doing during this process is diminish the strains. I'm controlling the strains. I'm diminishing the strains from the history of the strains was this one, I stretched up to here, and at this point I reverse the strains, and I go into that. In the reversal, I see that this is keeping constant. But what happens when I arrive back to this point in terms of the strains? How much are the strains?
So there is no permanent
No,
deformation?
no. There is, I didn't say this. There is no, as you say, there is no permanent deformation in this that is specific of these damage models, in contrast with the ones that we'll see later, which are the elastoplastic models. Okay? So that's why, for instance, for metals, this doesn't work. Because metals are characterized by that. But what are called quasi-brittle materials, they are like that. Materials that break very soon. But they break very soon, they follow this way. Certain point they break and they go back to zero stresses. Okay?